This particular screencast will have a few questions, a few problems from the extra class worksheet in the topic of statics, and I want you to approach this screencast as if it is an actual lecture. So listen to the screencast very carefully, and you should also take notes in your classwork notebook. If you want, you can stop or pause the screencast from time to time. You can replay bits of it if something is not clear, but finally you should have a set of complete notes corresponding to the problems that I discuss in this particular screencast. Now we'll start with the classwork question, the extra classwork question number 30 in the extra sheet which I have given you on static equilibrium. The question is as follows: a circular roller of weight 1000 newtons, so that's the weight 1000 newtons, and radius 20 centimeters hangs by a light rod AB, and the length of the rod is given to be 40 centimeters. So that's the length of rod AB, that's the radius of the roller. A roller is essentially a cylinder, and the roller rests against a smooth vertical wall at point C as shown in the figure. Now if you look at the figure, you see that at point C the roller is resting against a wall. You can see that it's described in the question, and the wall is smooth as given in the question. So immediately what must come in our mind is, if the surface against which the roller is resting is smooth, the only force which the smooth wall can exert on the roller is a normal reaction. Friction cannot be exerted because the wall is smooth. So that's the physical diagram which I have drawn. And what else is given in the question? Well, you have to assume, the last sentence says, you have to assume that there are pin joints at A and B. So this is point A, that's one of the pin joints. This is point B, and that's the second pin joint. And these pin joints are given to be smooth, so they can't exert any friction. And what are you supposed to find? So you're supposed to find what is the tension in this particular rod, and secondly you have to find what is the reaction of the wall at point C, that's point C, and what is the force exerted by the wall on the roller at point C. These two forces you have to find. Now as usual, we begin by drawing the free body diagram of some part of the system. In this case, it could be the free body diagram of the entire system consisting of the roller, this roller, and the rod taken together. You could try it that way also. I think you'll get the answer. But what I will do is I will draw the free body diagram of the roller first, and after that I will follow it with the free body diagram of the rod if needed, and let's see whether we can solve it that way. So I've drawn the roller, and the forces on the roller are, number one, the weight of the roller. Now that's given to be 1000 newtons, and assuming it's a uniform roller, the weight will act at the center like that. So weight 1000 newtons, it's the weight which is W. Now the other force acting on the roller is the normal reaction exerted by the wall at point C. Remember, we have said that the wall is smooth, and therefore the only force exerted by the wall is the normal reaction. There's no friction. This I'll call N, normal reaction exerted at C. And finally, we have to find the force exerted by the pin at point B on the roller. Now this rod is given to be massless. So you are aware that if you have a massless rod and there are forces acting only at its ends, then the forces must be collinear with the rod, assuming the rod is in equilibrium. And therefore we have done certain problems before in which we realize that this pin over here at point B, there is a pin, and I have separated the pin in this particular rough free body diagram. So this is only the rod. So the lower point is point B, and these are the forces exerted on the rod at the two ends. Now let's go to the pin over here. The pin experiences the same force, this force, but in the opposite direction. So this is a action reaction pair. The pin and the rod, they exert equal, opposite and collinear forces on each other, and the pin, which doesn't have any weight of its own, is in equilibrium. So that can only mean one thing: there is an equal and opposite force on the pin. So these two forces on the pin, they cancel. Now all these forces are equal in magnitude, this force and this force and this force and this force. And finally the pin itself exerts the same force by Newton's third law. That is, this force is exerted on the pin by the roller, and therefore an equal and opposite force must be exerted, equal, opposite and collinear force must be exerted by the pin at point B on the roller. So that's the roller, this is point B. So I want to find, well, actually this force I want to show it in the FBD, but I want you to note that this force is equal in magnitude to all of these forces, and its direction is of course the same as some of them and opposite to some of them, and it is this force which we will draw in the FBD. It's going to be directed along the length of the rod, of course, so it will be in this direction, and it of course has to be equal to the tension in the rod too. And now of course we have drawn all the forces on the roller. There are only three forces, and out of them we do not know the magnitudes of two of them, this one and this one, and everything else is known. The roller is in equilibrium, so of course we can apply, and we will apply, Lamy's theorem to find the unknown forces. So to do that, of course, we have to just draw the forces so that they originate at the same point. So that's the normal reaction coming from the wall, and that's the tension, the force of tension, and finally we have the weight W. Now this is given to be 1000 newtons, and we want to find the remaining two forces. Now if this angle is theta, and we actually do know this angle is also repeated over here, because the tension T, the force T, is collinear with the rod, so that's same theta. In fact, we can do a small calculation. You know that the length of the rod is 40 centimeters, so that's 40 centimeters, and the radius of the roller is 20 centimeters. So I'll just draw the radius. Remember, the radius is perpendicular to the tangent. The wall is the tangent, so I must draw something perpendicular to the tangent, and this radius is given to be 20 centimeters in the data. So naturally sine of theta is the opposite side, so 20 centimeters by 40 centimeters is the hypotenuse, so that's half, and I get theta as 30 degrees. Okay, so for our reference I'll just put theta over here, that's 30 degrees. And now I'm in a position to apply Lami's theorem to these three forces. So let's see, 1000 newtons divided by, now it's the sine of the opposite angle, so it is this angle, sine of 90 degrees plus theta, sine of 90 degrees plus 30 degrees, equals T divided by, now the opposite angle is this angle, it means the angle between the two remaining forces. Now that's 90 degrees, so sine 90 degrees equals, and the third force is the normal reaction of the wall, so that's NC divided by the angle between the remaining two forces is this, it's sine of 180 degrees minus theta, 180 degrees minus 30 degrees. Now sine of 90 degrees plus 30 degrees is cos of 30 degrees, so this I'm going to write as cos of 30 degrees, and cos of 30 degrees, as you know, is root 3 by 2. Similarly, sine of 180 degrees minus 30 degrees is the same as sine 30 degrees, and sine 30 degrees is half. So this entire equation can be rewritten as follows. I can just simplify by taking this 2 to the top, so 2000 divided by root 3 newtons equals T upon sine 90 degrees is 1, need not write it, equals, I take this 2 to the top, so it becomes 2 times NC. And you see that I can solve for T as well as NC. In fact, I've got the answer for T. T directly I can write it as 2000 divided by root 3 newtons, and similarly NC I can write it as 1000 divided by root 3 newtons. So if you go to the diagram, the NC which you have calculated as 1000 upon root 3 newtons, that is this particular force. It's nothing but the push, the normal push exerted by the smooth wall on the roller. It's the normal reaction, and that's one of the forces that we wanted to find. Now the second force which we have found, we have called it T, it's 2000 upon root 3 newtons, and although it is the force exerted by the pin at B on the roller, we have proved previously that it's also equal to the tension in the rod. You can imagine that the rod is cut at any point and you get the same value of the tension, and that's equal to T. So the tension in the rod is 2000 upon root 3 newtons. That's because the rod is massless. The second way to solve the problem would have been to draw the FBD of the entire system. So you have the roller here and you have the rod here, so everything is included now. You could exclude the pin at this point, don't include it, you need not include it in the system, but the pin at the other end, that is at point B over here, you do include it, pin is included. Now what are the forces which are acting on the system? So number one, the weight of the roller is 1000 newtons, that acts at this point, weight is 1000 newtons. Remember, you have to include only the external forces acting on this system, and weight definitely is an external force. you have the normal reaction exerted by the wall at C, so this force NC, and finally at end A the pin pulls on end A in a direction which is collinear with the rod, and that force, as we know, that is in magnitude equal to the tension in the rod itself. Now you do not include the forces between the pin at this point and the roller because they are internal to the system. So there are exactly three forces acting on this system, and the system is in equilibrium. Now you realize that these three forces, if you slide them and you originate them from the same point, if you make them originate from the same point, you can always do that, that's allowed if you want to solve by Lami's theorem. So you get T here, you get NC like that, and you get W in that direction, and this angle already it has been proved, it's theta, which is 30 degrees. Now you see that this diagram is no different from the diagram which we drew earlier, and therefore the solution will be the same. That's another way to solve the question. So with this we can now turn our attention to the next question, and that's question number 31. Now in this question, I'll just read it. A sphere of weight W is held between two smooth plane surfaces as shown in the figure, and you have to find the reactions exerted by the surfaces on that sphere. Now the surfaces, one of them seems to be vertical, it's like a wall, and the sphere is somewhere over here like this, and the other surface is like an inclined plane, so its inclination with the wall is 30 degrees. This angle is given to be 30 degrees. These are the two surfaces, and they are given to be smooth, there is no friction. The sphere is held by them, and we have to find what are the reactions exerted by the surfaces on the sphere. Now of course the spheres, since they are smooth, they cannot exert friction, and therefore the only force that it is possible for each surface to exert on the sphere is a normal reaction. So I'll draw the FBD of the sphere in this physical diagram itself. One of the forces is this one, so that's the normal reaction exerted by the left surface, so I'll say NL, L standing for left, and the normal reaction exerted by the right hand side plane is this one. It's normal, it's along the common normal to the sphere and the plane, that's NR. And the third force is the weight of the sphere, which, assuming the sphere to be uniform, the weight acts at the center, so it's acting over here, and that weight is given to be W. And once again there are three forces, and the only known magnitude is W. The other two magnitudes are unknown, but the directions of all of these forces are known. So you can solve by Lami's theorem once again, and please note that in this question as well as in the previous question you can solve both of them by sigma fx equal to 0. So that means the horizontal components of all forces add up to 0, and sigma fy is equal to 0. Now that approach is equally valid. You will get the answer, or you can solve by Lami's theorem. So as a variation, maybe in this particular question, instead of solving by Lami's theorem, I'll solve it by sigma fx and sigma fy equal to 0. So whatever approach I I adopt, I must find the angle made by this particular force with the horizontal or with the vertical. Now a bit of geometry will tell us the value of this angle. Let's see. This line, which is horizontal, is perpendicular to this line, which is vertical, and this line or this direction is perpendicular to this. So I've got a pair of lines which is perpendicular to another pair of lines here, and therefore the acute angle between them must be the same. So the angle I'm trying to find out, this angle, must be 30 degrees. So let me try and solve the question. I can say sigma fx or fy equals 0. Now why did I start with sigma fy equal to 0? It will give me a bit of an advantage. You can start with sigma fx also, but if I write sigma fy equal to 0 first, the advantage is that this unknown force, it has a y component, but this unknown force doesn't have a y component, and therefore in the sigma fy equal to 0 equation, only this force will appear and the other unknown force doesn't appear. W will appear, of course, and therefore I get the value of nr directly in one step. The equation itself involves W and nr. That's the advantage of writing the sigma fy equation first, although you can do it by sigma fx is equal to 0 first. The only thing is you will have to write the second equation, sigma fy equal to 0, after that, and then solve them simultaneously. Okay, now sigma fy equal to 0. Let's take upward direction as positive, and let's look at nr first. So nr sine 30 degrees is the y component of that force, and the only other force, as said earlier, which has a component in the y direction is W. In fact, it is entirely in the negative y direction, so minus W equals 0. Now nr multiplied by sine 30 degrees is half. I take W on that side, is W, and this implies that n, the normal reaction exerted by the right hand side wall, that must equal 2 times W. So that's the first answer. It's a simultaneous equation, but I've got directly an answer actually. Now W is a constant, it is given, so don't think that we have to find W. Now sigma fx is equal to 0 is my second equation, and I'll take rightward as positive. It's not compulsory, but that's the convention, so I'll follow it. You can take leftward as positive too. Now let's see, NL plus NL because it is rightwards. Now W doesn't have an x component at all because it is vertical, so I leave that out. And NR, it has an x component but it is leftward, so I put a minus sign. Minus NR into cos of 30 degrees is equal to 0. That's my second equation. So you have two simultaneous equations. You can solve them by your normal rules, but luckily we have written this particular equation, the nr equal to 2w equation, first, and we have got the value of nr here directly. We can substitute it in equation number 2, so we get nl, the left surface's normal reaction, minus nr is 2w into cos 30 degrees is root 3 by 2, that's equal to 0. 2 cancels. This implies that NL, the normal reaction exerted by the left plane, is root 3 multiplied by W. That's how to solve this question using sigma fx and sigma fy equations. Can solve it using Lami's theorem too. You'll get the same answer.